Right. Well, many thanks for the invitation. So I apologize if this will not be right in the core subject of the workshop, but it's still, I will be talking about some variational problems motivated by biology. So let's see how this, somehow it doesn't move. Maybe it's another one. Yes. Mhm. Okay. So in particular, I will be talking about optimal shapes of tree roots and branches. So can we identify payoff functionals and cost functional which generates shapes like this or like this as optimal solutions? So that's the starting questions. Okay, so let me start with some obvious remarks. So first, that biology is immensely complicated. So to formulate a tractable mathematical problem, we need to identify a few essential features and remove everything else. So what we want to do is introduce functionals that measure the efficiency of various shapes, study the corresponding optimization problems, and then eventually compare this minimizer with shapes observed in nature. Okay, so let's start right away with how do we formulate an optimization problem for tree branches. So the basic object will be a measure, a positive random measure that would be the distribution of leaves in 2 or 3 dimensional space to be optimized among all positive random measures supported in R3+, that is above ground. Okay, a payoff functional would be a functional of the measure mu that will measure the total amount of sunlight collected by the leaves. And the cost functional will be what I call irrigation functional for mu, which describes the cost of building a network of branches that sustain the leaves and transport water and nutrients from the base of the trunk to the leaves. Okay. For example, we could spread out the leaves far and wide, right? Then they will collect a lot of sunlight, but then we have to pay a lot to construct all these long branches that sustain the leaves. Or else we could clump all of them in a very small region, and then the transport cost will be very small, but it will collect very little sunlight. Okay. Just intuitively what's going on. What is a sunlight functional? For example, let's assume that rays arrive with a fixed angle. Let's say that the sunlight arrives parallel to the unit vector n, so in this direction here. This would be the subspace orthogonal to n, and phi of x would be the density of leaves at a point x. So phi of x tells me where there are more or less leaves, right? So if we want to look at how much sunlight reaches a point y plus Sn, so for example, reaches this point, well, it depends on how many leaves there are on top of this point. So you follow, for example, these light rays. Some of them will be collected here, and a few will go through, other will be stop collected here, and other will go through to the ground. All right. So in the end, a reasonable formula would be the sunlight that reaches this point here would be the exponential of minus the integral of all the leaves which are above this one, right? And then the total amount of sunlight will be given by a functional of this form. You just integrate over the whole distribution of leaves. How about tree roots? That's a different thing, of course. So again, the basic object will be a measure, this distribution of root hair cells, the one that suck, collect water and nutrients. from the ground, and this is to be optimized among all positive measures supported in R3-, that is below ground, of course. The payoff will be now a harvesting functional, which measure the total amount of water plus nutrients harvested by the roots. And the cost functional would be, again, the irrigation functional of this measure mu, which now describes the cost of building a network of roots transporting water and nutrients from the tip of the roots to the base of the trunk. So how do we define this payoff functional? Well, let's say U of x is the density of water and nutrients in the soil, just one single function. We are simplifying at most, of course. Phi of x, again, is the density of root hair cells. Okay, so the density of this measure. At equilibrium, U, the density of water and nutrients, would satisfy this elliptic equation. So there will be a diffusion, there will be a source, and there will be an absorption, which is the density of water times the density of root hair cells, how much it's sucked, right? And in this case, the total amount of water and nutrient harvested is just the integral of this term here, how much we collect, right? Okay. Now, the most important part and the most tricky of these three functional is the cost functional. How much do you pay to construct a network of branches to transport water, for example, from the base of the trunk to the tip of the leaves, right? So the first example of this irrigation problem actually goes back to Gauss, although it's called Steiner problem. And the problem is this. So assume that I have a well located at one point, let's say point P note, and I have a number of houses that require water, and I want to construct a pipe, a system of pipes that connects P node with all these houses. What is the minimum length of these pipes that achieve this, right? That is the original Steiner problem. And you can see from this picture, the optimal shape is something like this, where all these angles divide, are 2 pi over 3. So all these three angles have to be the same for optimality, right? However, this problem here does not take into account the flux that I am transported. For example, a more recent definition of transport problem, or ramified transport, is where the cost of a pipe depends not only on the length, but also on how much is the flux, how much water you are transporting it, right? And so the cost of the pipe will be the length times the flux to some power alpha, where alpha is between 0 and 1. Why alpha? Well, you can think that the flux will be proportional to the area, to the cross section, right? So, for example, here would be pi r squared, right? But the cost for building it is the lateral surface. And the lateral surface is going to be the length times the square root of the flux. So it grows in a sublinear way with respect to the flux. For example, assume that I want to transport 2 units of water, one to here and one to here. So if I just build 2 pipes, I pay one for this and one for that. Okay. If I put them together at least part of the time, during this portion here, per unit length, I'm not paying 2, but I'm paying square root of 2. Here, alpha would be 1/2, right? So this ramified transport is trying to put together the pipes in let particles of water travel together as far as possible, because when they go together, I get a discount. That's the main thing. Okay. So when alpha is strictly less than 1, I get this economy of scale. Okay, so this is what initially was a problem for irrigating a finite number of points, of point masses, and this has been extended to the problem of irrigating an arbitrary positive measure. Okay? And there are two different ways. Given any measure, you can approximate it with a finite number of Dirac deltas, in a weak sense. Or another way is the Lagrangian point of view, initiated by Maddalena Moren and Solimini, which you look at every single particle, psi, and you try to describe the trajectory of each water particle as it moves, let's say, from the well to the final location. For example, let's say I want to irrigate a measure which is uniformly distributed on this segment. So what can I do? Well, I start with my particles here, and they all travel up to this point, and then half of them go to the left, half go to the right? And then when we are here, half go to the left, half go to the right, and eventually you can see it's uniformly distributed over this segment, right? So the total cost, it will be an integral of the cost of transporting every single particle of water. So here, psi is a Lagrangian variable that labels each particle of water. Okay, so let me briefly state some existence result. I don't have much time here. So the first is about optimization problem for branches. Assume that this D is the dimension of the space, and this alpha is like the discount exponent. So the optimization problem for branches maximize the sunlight functional minus the irrigation cost as a solution mu star with bounded support. And in general, this is not unique because the problem is highly non-convex. There can be lots and lots of local. Yes? No, in fact, next slide, I'll explain this. Yes, yes. And another is the optimization for roots. If you want to maximize the harvesting functional minus the transport, again, this has a solution, and the optimal measure has bounded support. Okay. Why is this assumption here? Well, there are two constraints. First of all, for the sunlight functional, the distribution of the measure must be at least d minus 1 dimensional. Because, for example, if I put the measure just at 2 points, it collects 0, right? On the other hand, if it's too much spread out, the cost of irrigating this becomes infinite, right? So that inequality is necessary, because if it's not, it doesn't work, then either the payoff is 0 or the cost is infinite. That's how it goes. See, the point is, I pay little if they are all go together. But over here, they have to travel on smaller and smaller pipes, right? And then the cost per unit length is very high if I'm traveling on small pipe. And that's why it can be infinite, depending on alpha and depending on the dimension. Okay, let's see. So these are just basic existence results based on lower semi-continuity results. Okay, there are a few results that we could prove on qualitative theory. So one is about, in dimension 2, what can we say about the optimal shape of 3 roots? So assume that alpha is between 0 and 1. Then in dimension 2, the support of the optimal measure is nowhere dense. So what does it mean? It means that I don't need to construct roots that cover the whole space, right? Over longer distance, water and nutrients might be transported by a root system, but at small length scales, it's more efficient to rely just on diffusion. So I don't need to construct these roots on everywhere. They just can reach every point within a distance epsilon. You can think like this. And this is one of the deeper results, that is, this is obtained by a careful analysis of optimality conditions. So, you see, let's say I have an optimal measure mu, and then I make a small variation. I test optimality by performing a small variation. So assume that I add an infinitesimal mass located, let's say, at the point x. How much does the payoff increase and how much does the cost increase, right? So phi of x would be the additional harvesting payoff if I add a unit mass here, and z of x is the additional transportation cost if I add a mass here. And optimality condition would be that phi has to be less or equal than z of x for every x, otherwise I would improve by adding a mass here. And phi of x has to be equal to z on the support of mu. And then a fairly long analysis shows that, let's say, this is one of the big branches where we are transporting the mass. So if we move away from one branch, then the transportation cost grows like, let's say, x minus x naught to the power alpha. So is small along the branch, the big branch, because moving along a big branch is cheap. If you want to move along small branches, then it's expensive, right? So if you move away, then it immediately becomes a lot more expensive, like x minus x naught to the power alpha, right? Alpha is small. And then when you solve the elliptic equation, it turns out by a Sobolev embedding, this function phi is much more regular. So phi of x minus phi of x naught is bounded by x minus x naught to some power beta, which is bigger than alpha. So the conclusion is that z grows fast, but phi does not grow that much fast. So I can find an open set very close to x naught where z is strictly bigger than x. When the cost is much bigger than the harvest, then it's not optimal to put any measure here. Okay, so on this open set, the measure has to be 0. Okay? And that is a sketch of the proof of this. On the other hand, about the optimal shape of 3 branches, with the definition we had so far, it turns out that actually you don't really recover a shape of a tree, but what you recover is the shape of a solar panel. Okay? So clearly there is something missing. For the roots, it's pretty much on what we want, but for trees, it's clearly some factor is missing from the model, because if the rays come with this angle here, for example, the optimal shape is something that is constant here and another segment here. So the optimal positioning of solar panel is very different, for example, from the orientation determined by phototropism. Okay, so I leave this as an open question. How can you determine some mathematical model that justifies phototropism? A simpler optimization problem that yields more realistic shape is this. So find a positive measure that maximizes this functional here, but the harvesting functional could be something of, actually this would be simpler form. So this would be just the total mass of the measure, the total amount of leaves, and this is a penalization for concentrating a large amount of mass in a small space. So you don't want to just clump a lot of leaves in the same space, because then they would not have not only sunlight, but also oxygen, air, and so one function that gives more realistic shape is this this kernel here. Simply, you can take k of xy is some constant times e to the minus x minus y. So what does this mean? It means that when x is close to y, this is penalized, right? So you want to spread the measure mu wide, because if you clump them like in a Dirac delta, you pay a lot in here. But when x is far from y, you pay almost nothing. Okay? So that penalizes clamping a lot of mass in the same place. Okay, so let's see, I have still a few minutes. So the second part of this talk would be on more recent work about computational algorithms. So first, let me say that this is a very tough numerical problem, not only analytically, but I would say numerically it's harder. And the problem is that the irrigation cost is lower semi-continuous, so it's not even continuous, and it's non-convex, so it might have a lot of local minima. So you don't want to get stuck immediately in one of these hundreds of local minima. Okay? So how can we approximate with smoother functionals? One possibility, which was explored by Uday and Samtambrogio some years ago, is you want to mollify, approximate this functional with something which is nicer, more regular, right? So this is following an Eulerian approach. So you think of the original problem in a space of vector valued measures. So the original problem refers to measure describing the flux of water, let's say, from the origin to the various leaves. Okay, so in this case, for example, what is the flux? Well, the flux is zero everywhere except on this segment, this segment, this segment, and so on. So it's a measure, a vector measure, but concentrated on a finite number of segments, right? So very singular. On the other hand, we want to approximate this with fluxes that live in a space of smooth functions. So I want to, well, first of all, I smooth out, I replace a Dirac delta here with modification, so a measure distributed on a small disk, right? And here the same. Here we have three sinks and a source, and we replace the sinks with, well, three disks, let's say. And then we want a flux so that the divergence is, here is positive, and here is negative, right? And so among all the vector fields in H1, such that the divergence is this modification minus these three modifications, minimizes this functional here, which is a Modica-Mortola type problem. And, well, it's hard to guess what it should be if you are not an expert like me in elliptic equations. So this part tries to penalize the big gradients. But, I should, not that technical. What happened? Okay, thanks. Okay, so here we are penalizing a big gradient, but of course this comes with epsilon. So as epsilon is small, we penalize this less and less. In fact, it has to become singular in the limit as epsilon goes to 0. And here we are penalizing some v, the integral v of x to the beta along in the x times e to the gamma. And of course, beta and gamma has to be very precise constants. And for these special constants, it turns out that gamma convergence holds in dimension 2 when alpha is between 1/2 and 1. And I guess more recently, there are more general results in this direction. So this is a way of mollifying, replacing this ramified transportation cost with something which is smoother. Okay? What we have done recently with one of my postdocs, Giacomo Vecchiato, is to mollify, again, this ramified transportation cost, but from a Lagrangian point of view. So the Lagrangian point of view was, as I said, introduced in this paper. So psi labels one single water particle, and T of psi t is the path of the water particle parameterized by arc length. So one water particle, for example, goes here, and another one goes here, and so on. Okay. So what is the cost of each path of the water particle? Well, to find this cost, we have to find if they are traveling on small pipes or big pipes, right? Big pipes are cheap, small pipes are expensive. Okay, so for every point x in space, we define the multiplicity as the total amount of water particles that travel through this point x. So here there are a lot, here there are less, here there are less, right? And then the irrigation cost is an integral, and here you see this thing is the multiplicity to a negative power. That means if the multiplicity is big, we pay less. Okay? So this is a way to measure the same irrigation cost. Okay? So what we are doing is modify this multiplicity here. So we take J epsilon is this function here, the maximum between 1 and 1 minus x over epsilon and 0, and define this modified multiplicity. What does this mean? Well, it means the modified multiplicity at the point x is not just the amount of particles that go through the point x, but within a neighborhood of radius epsilon from the point x. Okay? So even if they are not exactly at the same point, we give them a discount anyway. Okay? That's the idea, right? And so then the modified irrigation cost is computed in this form. And one thing that we can prove is that in this case, the modified irrigation functional gamma converge to the original irrigation cost as epsilon goes to 0. And so how does this work? Let's see, for example, let's say I have two initial configurations. So the particle from here travel to A and then to 0, and this one go to B and then to 0. Right? If I perform a local gradient descent, how can I reduce the cost? Well, you see, as long as these two paths do not coincide, I still pay 2, right? It's only when they coincide that I really get the discount, right? So if I'm here, if I make a small perturbation, the only thing I can do to reduce the cost, it makes this straight, so the length is reduced, right? So I would recover as local minimum just these two straight segments. On the other hand, if I take this modification, then you see from here, I get the discount even if these are not coinciding, but if they are at a distance epsilon from each other. Okay? So I have better chances of getting this shape here by a local minimization, which is the correct one. Okay? So I just conclude showing some numerical simulation done by Giacomo Vecchiato. So let's say I start with this initial configuration. If I take epsilon is equal to 1, then they tend to come together, but not that much, because if they have a distance epsilon from each other, they already get the discount. So they are not very motivated. to stick together, right? They are trying to simply become as short as possible. When I reduce the epsilon from 1 to 0.5 to 0.25, then they are really motivated and they stick together. And this is pretty much the optimal irrigation shape, irrigation pattern. Okay? And this is the same thing, but with alpha is 0.9. So what is the difference when you take these two exponents, 0.4, 0.9? Well, 0.4, you get a lot of discount putting them together. 0.9, you get a much smaller discount. So 0.9 means that you want essentially to minimize the length, right? So minimizing the length, you get some pattern like this. And instead, in here, for example, you don't care that much in minimizing the length. For example, this one, instead of going straight down, it makes a much longer path, okay? But it's good because you get a lot of discount. That's the difference. While here, you don't get so much discount. Okay, last slide. These ones are simulation where I already am prescribing the measure to irrigate. So I'm starting with a measure that concentrates a finite number of equal masses over this circumference. If you want to optimize the shape of a tree, for example, then even the measure is something that you have to determine, right? And so the measure itself changes in different iterations. Actually, here we are not minimizing the shape of a tree, we are just minimizing this harvesting function, or the simplified one. So you want the total mass minus a constant times this penalization. Penalization means we don't want to clump the mass in a small region, okay? So these are three stages of the optimization algorithm. So we start with a distribution where all the branches are these segments. And then after one iteration, for epsilon is 1, we get these ones like that. Okay? Epsilon is 1 means that you get a big discount even if they are at a distance 1 from each other. So they don't care that much of merging together these branches, right? If I take epsilon is equal 0.5, then you can see they are trying to travel together. And when I get epsilon 0.25, they are even getting much more clumped together, these branches, except for the tips. Okay? Of course, one of the things that we would like to do is change the functionals and see if by changing the functional we can get shapes of different trees, for example, like weeping willows or poplars and so on. In fact, the cost of a branch should depend also not only on the length, but also on the inclination. Like building a branch going downward should be cheap. A branch going horizontally should be much more expensive, and so on. Okay, unfortunately, Giacomo Vecchiato just got a position in a private company in Italy, and so I lost him after one year, so now I'll have to find another postdoc to continue the work. Well, thank you for the attention.